All right, very good. So welcome to the second lecture of the GPU programming class. So today we're going to talk about like a CUDA programming model. So I'm going to introduce you the CUDA programming model, how you can think about programming when it comes to writing CUDA code, and also some fundamentals of data parallelism. All right, so in particular today, I talk about data parallelism, CUDA programming model, and also general GPU programming workflow. Okay, all right. But before we start, I just want to mention something. So in this class, we mostly focus on CUDA, but you should be aware that CUDA is not the only way to write general purpose programs on GPUs. So there are some other GPU parallel programming frameworks, such as OpenCL, which is open source, and OpenACC, which is another framework, but it is not similar to CUDA. OpenCL kind of similar to CUDA, but OpenACC, you just write compiler directives. It is similar to OpenMP if you have worked with it. And then there is HEAP, HEAP, which is mostly used for AMD GPUs, and also NCCL, which is used for writing multi-GPU applications when it comes to NVIDIA clusters. But in this course, we focus on CUDA, but using the others, it's kind of similar. Not OpenACC, but OpenCL HEAP is kind of similar to CUDA. All right, so apart from CUDA for GPU programming, there are some other frameworks that are used for parallel CPU computing. Among them, you can see like MPI for distributed memory machines, and also OpenMP for shared memory machines. And both MPI and OpenMP, they can be used with CUDA. Okay, so in the parallel programming course, we usually cover OpenMP and MPI. And here, CUDA. So you can basically combine these things depending on your application. Okay, so let's just start with different types of parallelism that usually we have in the applications and see what the GPUs are usually designed for when it comes to parallelism. Because the main reason that we use GPUs is to gain the hardware capabilities to parallelize our applications. But the applications also should have some parallelism inside them. Okay, so most of the time we can see two types of parallelism. One of them is called task parallelism, and the other is called data parallelism. Okay, so these are two major parallelism types that you can see in the applications. So in task parallelism, what you have is the following. So you have two, like not two, but you have like some tasks that you want to execute independently and in parallel, right? So for example, here we have a task. Let me just do it. So here you have, for example, you have three tasks: task A, task B, and task C, right? Task A and B can use like some data. This data can be shared between those tasks, and task C can use another kind of data, right? So what you have in task parallelism is that you want to wrap like these tasks into some like software component, like an object or a function or something like that, and then you want to execute them in parallel on different threads. So you basically assign a thread to a task, and then that thread will execute the task, right? And it's done in parallel. Okay. On the other hand, in data parallelism, you have a lot of data, right? You have so many data, a huge number of data points, and you want to perform the same operation on these data points, right? So basically, you have the same task, right? But you want to apply it on different data. right? And this data can be huge. And that's kind of typical in machine learning applications, where you want to do something, to do some like data processing, but you have a huge amount of data. So that's called data parallelism, applying the same operation on the same data, and you can see it in different granularity. So that data can be like a floating point number, or it can be a matrix or tensor, or even larger. Okay. So now I have a question for you. Can you make an example of task parallelism and also data parallelism? Anybody has any ideas?
Is my mic working?
Yes, it is working.
Yes, okay. So for the task parallelism, maybe calculating the variance of a data set and the standard deviation.
Yeah, you can do it, but in different tasks. But still, it is something that you can do with data parallelism, right? So just two operations like sequentially. Like for task parallelism, usually the tasks are kind of independent, right? So for example, when you are working with like, I don't know, Microsoft Word, so you have one thread that is like receiving your inputs from the system, and you have another thread that's just checking your your text, right? So there are two tasks. Or for example, when it comes to gaming, you have like one thread will uh, process the sound, another thread will process the gameplay, another thread perhaps performs some kind of communication with the server and things like that. And another example of task parallelism is web servers, where you have like different user requests, and then you wrap them into different tasks, and then each task is executed on a different thread. Okay, so this is mostly what is done in task parallelism. All right. Okay, just now I have an interesting question. So assume you have a system, right, that has 10 cores, right? And each core runs one thread, right? So 10 thread, 10 hardware threads in total. And you have more than 10 tasks, like you have like, I don't know, 50 tasks, right? So how usually you execute these 50 tasks on these 10 cores kind of efficiently? What ideas do you have for this kind of scenario? When the number of tasks are more than the number of cores that you have. Any ideas? Okay, yeah. Well, in that kind of scenario, you can create something called a thread pool, right? Which is uh, which is an asynchronous queue. Then you push in the tasks, like task T will be in the queue, right? And then you have different threads here. So this is the task queue where you push in the tasks, like task one, task two. And then you have a thread pool here, or a thread queue. So you have different threads here, and each thread will fetch the task from the queue and execute it, right? So if you have 10 threads, it means that you are executing 10 tasks at the same time out of, for example, 50 tasks that you have in total. So thread pool is one of the most like important software design patterns when it comes to concurrency and task parallelism. Okay, outside. Anyway, all right. So now let's talk about data parallelism. So is there any application that you probably have in mind that is data parallel, not task parallel? Anybody has an example? Let me like make a simple example. Assume you have two vectors, right? And it has some elements, and you want to add these two vectors or two arrays, right? Okay, so is it a data parallel program or task parallel program?
Data parallel.
It is data parallel, yes, because you have a single operation, which is add operation in this case, and you want to add different data, right? Okay. And the same thing is true for like AI applications when you have a huge amount of data and you want to apply and you want to process them, right? Okay. So now, based on our previous discussion on GPU's throughput-oriented design and CPU's latency-oriented design, do you think GPUs are suitable for data parallelism or task parallelism? Which one do you think?
Data.
Yes. So because GPUs have a lot of threads, right? Then you can have these data, these huge data on these threads, and then you can perform the same operation. So all of the threads available in the GPU can perform the same operation on that huge amount of data. So that's why GPUs are very much popular in data processing applications, especially in AI. And for task parallelism, because you usually do not have a lot of tasks, so the number of tasks are not so many. And then latency is kind of important in that kind of application. So you usually use multi-core CPUs for task parallelism and GPUs for data parallelism. Okay. And then in the future, when we talk about the GPU architecture, you realize that GPUs are not quite suitable for task parallelism, even if you want to use them for task parallelism, because they use something called the single instruction multiple thread execution model, which means that all threads have to execute the same task. There are some techniques to work around it, but typically the GPUs are designed for data parallelism. All right. Okay, so we talked about this as well. All right, so now let's talk about this very simple vector addition example and see how we can run it on the GPU and the CPU. So this program is basically called the Hello World program in the parallel programming. Okay, so that's quite simple program. So you have an input vector X, you have another input vector Y, and you just want to sum them up element by element and generate the output vector Z, right? All right. So when it comes to CPU, so it's quite simple. So we can write a vec add function, right? So we pass in pointers to float. So just to write an array of floats. So X, Y, and Z, and we specify uh, the number of elements like n, and then we write a for loop, right? And then we just add these elements. So this is done sequentially. So we go through each element of these arrays, right? And then we perform the sum operation, and then we go to the next element. So this is how you write a sequential code. for this program, right? So let me write this code uh, also for you. Then when we want to compare the GPU code, we can compare them more easily. All right, so just let me open my VS Code window here. Let me share it. All right, can you see my VS Code window?
Yes.
Okay, so just let me quickly set the program up. So it's going to be kind of a refresher for you if you knew how to write C code, and also it's going to be good practice. Okay, so let me first create like a Vec add file. So because we want to run it also on the GPU, like in some minutes, so I will create the file such that it's suitable for CUDA execution. So when it comes to CUDA programs, you usually extend the file extension is called is CU or CU. Okay, so this is a vec add.CUDA file that I have. So let's create the main function quickly here. Yeah, close this. All right. So okay. So for this vector addition function, I basically need three. What's this error for? I need three arrays, right? So let's do it quickly. So I just need to have pointer to float A, B, and C. All right, and let's define n as the number of elements in the array. So let's make it big, something like that. All right. Well, I still don't understand what's this. Okay. Yep. Let me see if I'm connected to the server. I guess so. Okay. So just give me a second. I have to be connected to the GPU server that we have. And let me fix it first. Okay, let me share again. All right. You still can see the VS Code window, right?
Yep.
Okay, good. All right, so let's allocate some memory for this arrays. So just need to call malloc. So first, let me import this standard library. Okay. Now we can. So basically, we are what I'm doing here. You should do the same when it comes to GPU. So we're going to talk about that, but it's good to remember these things. So I just call malloc for some memory allocation, and then I need n times size of float, and then I have to cast it to float star, pointer to float, right? And I can do the same thing for vector B and C, right? So let me initialize them. For I smaller than n, then I plus plus. Just need to for example, let's initialize A to be 1, and let's initialize B to be 2. So the sum would be 3, okay? All right, now let's write this vector addition in the CPU version. So vec add CPU, then just need to pass in the arrays. So I will pass array A, B, constant also C, and the number of elements, right? Okay. And then I just can have a for loop like here, like this one. And what I do is to uh, add them up. Let me format file installed. Okay, I don't have it here. So CI equals AI plus BI. Okay. So this is basic thing that you write for vector addition. So because I use malloc here, so the best practice is to like free memory after like you have allocate that. So just let me call the free function, free A, free B, and free C, right? So the same problems that you have with manual memory management in C is also there in CUDA. So it's good to take a look on the problems that you and the bugs that you might have when it comes to manual memory management, like allocating memory and then you forget to free or free the memory that is already freed and those kind of problems. All right. So then let me just call this wake add CPU with A, B, and N. Okay, so let me just compile the code, see if it compiles. So I will compile it with CUDA compiler. Don't worry about that for the moment. So we talk about that just in a second. But it is NVCC, NVIDIA compiler. Okay, so it's there in the system. So I just need to pass in wake add. And let me see if it compiles. What is the problem here?
No semicolons after your mallocs.
Ah, right, thank you. All right, what about now? Some problems in the for loop as well, I guess.
Also, I think commas instead of semicolons in for definition.
Yes, that's true. Yes, thank you. Yeah, I should use AI for this syntax thing.
In both loops, also in the CPU.
Yep.
function.
Yes, thank you. What about now? All right, still we have a problem here. What is it? Okay. All right, okay. So I think it works. Let's see if it runs. Okay, so apparently it's working correctly. So there's only one thing that I have to add here, which is timing. So let me enable so just to do it faster. Okay, so let's include time in C. And I just want to time this wake at CPU function. So clock the start. So you just start the clock, end the clock, and then you just compute the elapsed time, and then you can report it like in seconds, right? Just let me make it millisecond. But it should be times to 1000. All right. So let's recompile the code. Okay, what is it? Okay. Yep. Should now work. Okay. So yes. So for this vector addition, for that amount of data, you spend like 4.52 milliseconds. So this is our CPU version. So let's see how we can do it on the GPU, and we do it step by step. So let me just create here a GPU function. Yeah. Okay, good. All right. So this is just a stop for the GPU, we add GPU, and then we're going to implement it step by step. All right. So let's get back to the slides. By the way, that C implementation should be quite familiar for you. Is there any questions about the C code that I just wrote? All right, very good. Okay, so let me share my screen again. Let me share the entire window. Okay. All right. Could you please confirm if you can see the slides?
Yes.
All right, good. Thank you. Okay, so we wrote this CPU version of this vector addition program. So now we want to do it on the GPU. So let's do it step by step and see how exactly we can do this. So before doing that, we need to know how uh, a heterogeneous system, including CPU and GPU, is actually organized. So for that, we need to know the system organization when it comes to that kind of machine, and also the terminology. So in that kind of scenario, when you want to write a program that works on a CPU and a GPU, so basically you have a CPU which is called host, and most of the time the variables that live in the CPU memory are subscript with H. So just to show that they are host variables, right? And then you have a main memory which is also called the host memory, right? And then you have the GPU, which is called the device. So then similarly, you can subscript your variable with D letter, right? And then you have a GPU memory, which is called the device memory. Okay. So the host memory, which is the main memory, and the GPU memory or the device memory, they have separate memory spaces, right? Which means if some data lives in the GPU memory, you don't have access to that from the main memory. And if some data is in the main memory, you don't have access to that from the GPU memory. And if you want to do so, you have to explicitly move the data from the main memory to the GPU memory, or from the GPU memory to the main memory. Okay? So in that sense, a CPU GPU system is a distributed memory system where you don't really have access to the memory space of different processes. Okay? All right. So if you want to, as I said, if you want to transfer, if you want to use data on GPU or on a CPU, you have to explicitly transfer them from the CPU and from CPU to GPU, GPU to CPU. All right. So from the hardware perspective, uh, the question is how the CPU and the GPU memory are communicating and how the hardware enables this data communication and data transfer. Does anyone have any ideas how this is done, like, from hardware point of view? There is a bus, usually called PCIe. You can also have other things like NVLink, and this PCIe is responsible for make sure that this communication is done. So PCIe is the way that CPU and GPU are basically connected to each other. Okay. So I don't know, if you installed a GPU on the system, the socket that you install the GPU in, and it is on the motherboard, is the PCIe socket. All right. So let's see how we, like, from top level overview, let's see how we can program such a system. So there are different steps that we need to take when it comes to writing GPU programs. So the first step is to allocate some memory on the GPU, right? Because you want to process some data and that data needs some memory. So the first thing that you need to do is to allocate memory on the GPU, okay? And CUDA provides some specific APIs for this GPU data allocation. It's similar to malloc that we use for allocating memory on the main memory or on the host memory. But when it comes to CUDA, CUDA has its own API calls. Then the next step is to copy data from the host memory to the GPU memory, right? So you allocated data on the GPU memory, then you have to move the data or basically copy the data from the host memory to the GPU memory. Then you perform the calculations or the computations on the GPU, right? So you basically keep the data on the GPU and you perform all the computations that you want to perform on that data, right? So you do not like transfer the data all the time. So you just like transfer the data to GPU once, perform as much as calculations as you want to do, and then in the next step, after the calculations are done, you just copy the results from the GPU memory to the main memory of the system, and then you have to deallocate the GPU memory, right? Similar to what we did in the CPU code, but here you have this explicit data transfer between CPU and GPU, right? So like this, step 4 and a step 2. Okay. So let's see how we do it in CUDA. So CUDA provides some API calls if you like after you install CUDA, and then these API calls are known by the CUDA compiler. Okay, so CUDA malloc is one of these API calls, which is used for allocating memory on the GPU. It takes two arguments: the size of the data, similar to malloc, and also a double point pointer to the data that you want to the pointer that you want to allocate. So it's a pointer to pointer, right? Because CUDA malloc internally needs to manipulate the memory address, so you have to provide the address of that pointer that you want to point to your data on the GPU. Okay, and then it returns just an error code that you can check if the CUDA malloc is successfully allocated some memory. And for memory deallocation, so similar to the typical C program, you have CUDA free. So free is for like for the host memory, and CUDA free is used for device memory, for the GPU memory. And you just need to pass in the pointer to the data, right? Okay. And CUDA error is for just checking the. All right. So this was about how to allocate memory on GPU and deallocate memory on the GPU. So after that, we have to transfer data from CPU to GPU memory and from GPU to CPU memory, right? So CUDA API call for that is, sorry, CUDA API call for that is this CUDA memcopy, which takes basically four arguments. The first argument is the destination pointer. So the pointer that you want to send the data to. And then the next pointer is the source pointer that you want to copy data from. Then the size of data, and also this enum data type, which shows the kind of transfer, CPU to GPU, GPU to CPU, or CPU to CPU, or GPU to GPU. So you basically have four kind of transfer. CUDA memcopy host to host, if you want to copy data from one memory location to another memory location on the main memory. Then you have CUDA memcopy host to device. So this is used for transferring data from CPU to GPU. And then you have this CUDA memcopy device to host, which is used for transferring data from GPU to CPU. And then you have this device to device, if you want to copy data from GPU to GPU, right? So using this, so you allocate memory using CUDA malloc, you deallocate memory using CUDA free, and you transfer data using this CUDA memcopy. So the general workflow, like in code, would be something like this. So these lines for memory allocations, right? Here you have data transfer, and then you transfer the results from the GPU to the CPU, right? And then you just free those memories. So let's do it in our code as well and see how we can do that. Okay, so let me share my VS Code again. All right, do you see the VS Code window?
Yep.
Okay. All right, so let's write these allocations in this vec add GPU. So as we can see here, we pass three arrays, like A, B, and C. So by default, these are living on the CPU, right? Because we're passing them from here. We're passing basically these three arrays, which live on this CPU memory, right? On the host memory. So let's call this CUDA malloc, and for that, you just need to okay, let me see. CUDA malloc, right? So I just need to pass in the let me first this. So okay, it wrote everything for me, but I didn't want it. So I just need to first declare the arrays on the GPU, so like DA, DB, and DC, right? or you can also call it AD, like PD or CD, doesn't really matter, but usually it's a convention to have D on the device variables or device arrays or something, right? Okay. Now let's allocate some memory on the GPU. So I can call this CUDA malloc, right? And then I pass in the address of this pointer and also the number of bytes that I want to allocate. And finally, I have to cast it as a void star star. All right. So then I can do the same thing for the others. So just let me copy and paste because this writes everything for me. Okay. So this DB and DC here, right? So now I have this memory allocation, and you can also check for errors here. But we just assume that we don't do it now. Okay, so now that I have memory allocated on my device, so I have to move the data or transfer the data from the host to device, right? So then I call this CUDA mem copy. Just let me use and just I remove this part. Don't need it. All right. Okay, so I call this CUDA mem copy, right? I provide the destination pointer, which is this arrays on GPU, and then I provide the source pointer, which is A, which is on the system's memory, on the main memory, and the amount of bytes that I want to transfer, and then I just call this CUDA mem copy host to device, right? And I do the same thing for DB. I also copy the content of this array B, right, to this DB, and then I use this CUDA mem copy host to device because I'm transferring data from the main memory into the device memory, the host memory to the device memory. Okay, then we perform the calculations here. Then after the calculations are done, we have to transfer data or transfer results, which in this case, our results are stored in this array C. So I have to transfer the results from DC to C, right? From the device to the host. And I just call this, use this CUDA mem copy device to host here, right? And then I just call CUDA free to deallocate these memory locations that I had on my device. Okay, is there any questions about these allocations and deallocations? All right. Okay, so now the only step is to know how do we perform the calculations on the GPU. So this is the main thing that we want to discuss now. All right, so let's get back to the slides. Okay. So we have the allocations, we transfer data, we are going to perform the computations, then we will transfer the results to from the GPU to the CPU memory, and then we just deallocate, right? So let's see how we can perform that calculation. Okay, so this was the vector addition problem that we had. So when it comes to sequential code, we have to loop through all of the elements, right? And then sum them up one by one, right? So now I have a question for you. Now assume we want to execute this on a GPU which has thousands of threads. So how would you parallelize this program? How would you execute this program on the GPU device?
I would split up the vector x and y and assign the different parts to different threads.
Well, this is, yeah, that's true. That's the correct answer. But that's a strategy usually used when it comes to CPUs, right? Where you don't have so many threads. Assume that at least from CUDA programming perspective, that you have access to like a huge number of threads. So how would you split in that case? Do you need a for loop there? For example, assume you have n data points in your arrays and you have like n threads. How would you split the data to the threads?
We need a loop for that.
Do you need a loop?
I think so.
So what I'm saying is you have 10, let's assume that you have 10 data points in the array and you have 10 threads, right?
I guess just do one addition on each thread.
Exactly.
That's it.
Yes, exactly. So you basically don't need a for loop, right? In this case, because you can assign a thread, right? You can assign a thread to only one addition, right? So this thread only works on these data points. This thread also works on these two, and so on, right? So this is one of the advantages of the GPU, because from the CUDA programming model, you can see we don't have unlimited like number of threads when we talk about the GPU architecture. But from CUDA programming perspective, from the CUDA programming model, you can assume that you have access to like so many threads. And it is up to the GPU hardware how to allocate those threads. So that's why you can assume that you can use one thread per data point when it comes to even large data sets, right? Okay, so in this case, we can assign a thread to each element of this array. Okay. Since GPUs have so many threads, so CUDA provides an organization for the threads, so the developers can be easily understand how they can use threads for their data, right? So, and this organization usually is kind of fit into the data. Like if you have a two-dimensional data, then CUDA thread organization is 2D. If it is 3D at max, so your CUDA organization can be in 3D. But here our problem is in 1D, so because we have only a vector, so it's not a matrix, right? So let's see how in this case CUDA organizes the threads, okay? So basically, when you call a function on the GPU, so CUDA launches an array of threads called a grid, right? So to perform this calculation that we have been talking about, you need to run like n threads if you have n elements, okay? So this array of threads is called a grid in CUDA, okay? And the grid is organized or is grouped into something called blocks, right? So basically, when you launch a grid, you are launching a grid of blocks, and each block has some threads in it. So for example, in this example, we have a grid of 4 thread blocks, and each thread block contains 4 threads. Okay? We will talk about it more when we talk about the actual hardware architecture, but essentially, one of the reasons that CUDA creates these thread blocks is that within each block, the threads can collaborate to each other. So there's a shared memory inside each block. And if you want to, but between the blocks, the threads cannot communicate, right? So the threads within the block can collaborate on each other using shared memory. So this is why CUDA organizes threads into blocks. All right. So when you want to execute a function on your GPU, you just need to run a grid of thread blocks, and each thread within these thread blocks will execute that function, right? So let's talk about it in more detail. So how we can launch a grid. So that function that I was talking about, for example, in our example, is the vector addition function that you want to execute on the GPU, is called a kernel, right? So kernel is a function that is executed on the GPU. And for executing that function on the GPU, you have to launch a grid of thread blocks, and each thread within this thread block will execute that kernel function. Okay? So you can have different operations like implemented in different kernels. You can have add kernel, multiplication kernel. I don't know, when it comes to AI, you have convolution kernel. So many of these kernels are already implemented in like TensorFlow and PyTorch, but essentially they are low-level CUDA kernels. Okay. So in order to launch a CUDA kernel, you have to be able to configure how many threads you want to have within the block and the blocks, and how many blocks you want to use in your grid. And this configuration is done like this, right? So assume you have a vector addition kernel. So assume you write a kernel called vector addition. We will talk about how we can write this kernel. And now here we just want to know how we can launch this kernel on our GPU. So the only thing that you need to provide is the number of threads per block and also number of blocks, right? So we will talk about the number of thread per blocks, how you can fine tune that, but let's for now consider 512, right? So I consider 512 threads within each block, and assuming that I have n elements in my array, I can divide n by the number of threads per block to get the number of blocks in my grid, right? Okay, let's just think. Okay. So here I specify the number of threads per block and also the number of blocks. But there would be a problem if the number of threads per block is not the multiple of like the number of elements that we will talk about that. But now, for now, let's assume that number of threads per block is a multiple of n. So we have an integer value for the number of blocks. And then we have this funny syntax for launching the kernel, right? So within these three brackets, you provide the number of blocks, right? And the number of thread per blocks. And then you call this vector addition function with these arguments. So it is kind of similar to normal C function call, but you just need to provide the number of blocks and the number of threads per block before calling this function. So this is the main difference between calling a kernel and calling a normal C function. But keep in mind that we haven't talked about how to write such a kernel. It is only about, this slide is only about calling this kernel, not writing this kernel. Okay. So for calling this kernel, you just need to specify this information, and then you just call it like a normal function. Okay, is there any question about this kernel call? All right. So before implementing the kernel, let's just update our program, support it. Okay. All right, so here, after I have these allocations and memory transfer, so I would call the kernel. So the kernel is not available yet because we haven't implemented it yet, but let's just call it here. Yep. So we're going to have a vector addition kernel, right? Just let me remove this. Okay. So I can choose block size, number of threads per block for 512, and let's have this number of blocks just n divided by the block size. Okay. And then I can just provide the number of blocks and the block size. All right. So that's it. So now let's focus on developing this vector addition kernel. And that's the most important thing when it comes to writing code on GPUs, because all of these things that we did so far, they are like just configurations and just like pre-launch kernel steps. All right. So let's get back to the slides. All right, so let's see how we can implement the kernel. So as I mentioned, kernel is kind of similar to a normal C function, right? However, you need to kind of annotate it with this underscore underscore global underscore underscore keyword, which is provided by CUDA API. So if you annotate a function in C with this keyword, then the CUDA compiler will understand that it's a kernel and it's not a typical C function, and it should be compiled to be run on the GPU, not on the CPU. Okay, so it's a kernel. Okay, so now let's see how we can implement that kernel. So as I mentioned, CUDA organizes threads into grids of thread blocks, right? And then it assigns index to each block and local index to each thread. And also the API provides you with the number of threads in a block and the number of threads in a grid in at most 3 dimensions, X, Y, and Z. So in this example, we are just using the 1D dimension, but next week we're going to talk about how we can have this in multi-dimensions. So now let's not worry about multi-dimension grids, and let's focus on this one-dimensional grid, okay? All right, so we know that we wanted to launch, in this example, 4 thread blocks, and each thread block has 4 threads in it, right? So CUDA provides this grid dim that X, and X is the dimension X, the first dimension, and this grid dim.x will get you the number of blocks in the grid. So in this case, it gives you 4, right? And then it also provides block ID x.x, right? Which gives you the block index. So for example, if you are this thread, so in order to perform computations, this thread needs to know its position in the grid, like this global position in the grid. And for computing that global position in the grid, it needs this information. So it needs to know how many blocks are there, how many threads are within the block, and what are its own index within the block, and also what is the block index. So this block ID x.x gives you the block index, for example, for all of the threads, right? So basically, each thread, when it calls this code, will know what is the index of the block that contains that particular thread. Okay, then you have block dim.x, which provides the number of threads in the block. And finally, you can have thread IDX or thread index, which gives you the thread index. So the index of the thread within the block, right? Okay. So now let me ask you a question for an exercise. So assume I am this thread, right? And I want to know my global index, right? I want to know my index counting from the beginning. So how can I compute this global index of this thread given this information that I can get from the CUDA API?
Block index multiplied by the block dimension,
Yes.
and then add the thread index.
Yes, that's true. So with that, I will know how can I get access to the data in the array, right? So which data I have to get access to? I just need to find my index because, as I mentioned, like the number of threads in this case matches the number of elements in our data. So we have a one-to-one map between the threads, between the thread grid and also the actual data, right? So if I can find my index, I basically find the index of the data point that I want to perform the operations on. Okay. So with this simple formula, just block index times like the block size plus the thread index, I can find my global index. Okay. Very good. So let's get back to the vector addition example. So here I launch I launch a grid of 4 thread blocks, right? In this case. And I assume that the number of thread blocks kind of is a multiple of the number of threads per block. So far it's okay. So just what I need to do now is to find the global index of each thread and just perform a simple addition, as you can see here. So let's see how this kernel is implemented. So this is the kernel that I was talking about. So the first thing that I need to do is to annotate it with this global keyword, right? And then I can define it as a normal C function, right? What I need to do, because this function or this kernel is called by all of the threads that I have in my grid. So the first thing that I need to do is to find the global thread index, right? As you answered. And after I found the index, I just perform the calculation, simple addition. So I don't need any for loop here, right? Because I broke the for loop into the threads, and each thread is just performing this addition formula. Okay? I will implement it in a minute, but let's fix some other problems here. So let's talk about boundary conditions. So if you remember, I just mentioned that we assume that the number of elements is the multiple but the number of thread blocks is the multiple of the number of elements, right? But this is not always the case, right? For example, assume I have, I don't know, 1023 like elements, and I want to group them into 512 threads per block, right? So what I need to do is just to compute the ceiling, right? To round up, to launch like a grid with one more thread block, right? Just to support it. But when I do that, so when I use the ceiling and launch one more thread block, this happens. So assume the number of elements is not the multiple of number of threads per block. So I have to launch a new block here because I'm using like rounding, right? So I have two more threads that I really don't need. So they are redundant. So what should I do in this case? Anyone has an idea? That's very simple. So I do the rounding here with this just simple formula. You can just check it out yourself. And then I provide a simple if statement, and I perform this addition only for the threads that their index is smaller than the total number of elements, right? So I just perform the calculation for the threads that really have this index of the data. Very simple. Okay, so now let's implement it in our code. Okay, just let me find it. Okay. All right, so let's develop the kernel. So as I mentioned, we just need to specify this global thing. Yeah, and that did it for me. Okay, so I just have this vector addition kernel. I provide like the data, right? And I need to identify the thread index within the kernel. And then I check this boundary condition and I just launch, and I just perform the addition. And here in the configuration, I just can call it as I explained before. So just let me just fix this thing here as well. I guess that's this. Yeah. Okay, so let's now compile the code. By the way, let me take the do the timing as well. So just let me, yeah. Okay, I just call this vector addition, vector add on GPU, and then here I just allocate memory and all of these things, and then I launch the kernel here. All right, so let's see if it actually works. So I just use this NVCC, the CUDA compiler here. So it compiled. Let me run it. Okay. So the results might be kind of strange for you. So as you can see, the CPU time is 4.8 milliseconds, but the GPU time is 68 milliseconds. Why do you think that's the case? Why GPU seems to be slower here than the CPU?
It's the memcopy call back to the CPU.
Yes, that's true. So in practice, we don't use like this memcopy and like memory allocations for each kernel call. So as I mentioned, we allocate the memory on the device only once, and then we perform as much as calculations as we need to do, right? So we need to somehow get the timing for the kernel, right? Not for the entire thing, because the memory allocations and these things are done only once. And it's the kernel that we probably run in a loop and also want to perform calculation, and it does the actual calculation. So let's see how we can do it, how we can perform the timing for the kernel. So for that, you can use like normal C timing within the kernel, but it's always best to use CUDA functionalities. And CUDA functionalities for timing the kernel that I would recommend you like to use it in your assignments and also in your project is called something called CUDA event. So you basically with CUDA event, you can define different events, and then you can measure time difference between those events. So let's see how we can do that. So I just want to time this kernel, right? So what I do is I just create two CUDA events, like let's see, CUDA. I guess the syntax is event. Yes. So I create a start and a stop event, right? A start for starting the kernel and a stop when I want to stop the kernel. The kernel is done, basically. So I just declare these two event types, and then I have to create them. So CUDA event create start, and then CUDA create event create stop, right? And then I have to record the timing for the event. So right before I launch the kernel, I call this CUDA event record to start the timing, and then I stop CUDA, and I call this CUDA event record for the stop event when the kernel launch is done. And I just use this CUDA event synchronize. I will talk about the synchronization, but basically it means that it waits until the kernel launch is over, because the kernel is launched on the GPU, and it's an asynchronous call. So we will talk about these things. But just for now, you should understand that you can create something called CUDA events, and then using these events, you can just record the timing. Okay, so now let's report the actual elapsed time. And for that, you just need to specify like a float just to store the results, and then you can call this CUDA event elapsed time, right? You specify this millisecond, the float variable, the start and the stop, and then it gives you the kernel execution time in milliseconds. Okay. All right. And finally, you have to destroy those events because they also have some internal allocations. So CUDA event destroy start and CUDA event destroy stop, right? So there are some steps for this CUDA timing. So you create a start and stop events. So you have to first declare them, and then you create them. You record the timing. Then you perform this synchronization because CUDA kernels are asynchronous calls. We talk about it like next week. And then you report this CUDA, and then you like report the timing using this CUDA event elapsed time, right? And then you destroy the CUDA events that you have created. To make sure that this works for like a lot of kernels, you should do some software engineering and then try to organize these things more properly. But for this simple vector addition function, that's going to be enough. So let me compile. Yes, so it compiled. So now let's launch it. And now you can see the actual result. So you see that for this particular problem, the CPU timing is 5.3 milliseconds, but the kernel, like the GPU timing, so the kernel time is 0.15 milliseconds, right? So which is dramatic decrease in the execution time. And given all of the allocations and everything, you have we have spent like 55 milliseconds. But that's the important timing for us is the kernel execution time, which is much faster than the CPU. All right, is there any question here? Okay. All right, so I think that's enough for today. So next week we're going to talk about some internals of the CUDA compiler, how we actually NVCC CUDA compiler compiles your program. And also we will talk about two-dimensional grids and how you can like process two-dimensional data like images and things like that using CUDA. And about the first lab, so I tried to release a lab 1 today, and the deadline would be until next week. So you're going to have 1 week to work with lab 1, and I try to provide the instructions for using CSC GPUs for the lab 1. And I highly recommend you to watch that CSC workshop for the parallel programming course to understand how you can set up your profile and then how you can like request the resources and things like that. Okay. All right. Any questions about these logistic things? Okay. So I think we can stop here and have a nice rest of the day.
Bye.
Bye-bye.